We've just finished reviewing the basic supply and demand model from Intro with an added level of mathematical sophistication. We've been fairly loose, though, about where supply and demand come from. In terms of the demand curve, I've been giving you some equations for the demand function in terms of things like price, income, and other exogenous variables. But we haven't really justified where we're getting these equations from, except for sort of appeals to intuition. Now is the point where we begin to develop a model of how individuals make choices. Since individual buyers add together to generate the market demand curve, what we're doing in this video is providing sort of a more rigorous and thorough foundation for the market demand curve. And the way we're doing this is by introducing two primary concepts. One is the utility function, and two is the budget constraint. And what we're doing here is our first real departure from what you've seen in Intro up until this point. First, we're going to begin with three basic assumptions. So the first is that any individual has tastes or preferences that determine how much pleasure they get from consuming different goods and services. Number two, consumers face constraints or limits on their choices. So in the model we're going to be working with in this video, that's primarily income. And three, consumers maximize their pleasure from consumption given these constraints. So first, let's define preferences. By preferences, we mean how a consumer ranks available alternatives. We can describe how a consumer ranks different goods using what we call a preference relation. Preferences are a ranking of different combinations or bundles of alternatives. And there are three preference relations that we typically use. The first says that A is at least as highly ranked, or what we call weakly preferred, to B. 2 says that A is strictly higher ranked, or strictly preferred, to B. And 3 says that A and B are equally ranked, or indifference. With these three preference relations, we can articulate three assumptions about consumer preferences. These are what we call consumer preference primitives. One is completeness. So any A and B can be ranked by any one of the three preference relations. 2, transitivity. If A is weakly preferred to B and B is weakly preferred to C, then it must be that A is weakly preferred to C. And 3, non-satiation. In the textbook, this is called more is better. Whichever terminology you prefer, it's fine. Number 3 says that more of a good always makes a consumer at least weakly better off. This is pretty plausible, especially if you say that getting rid of unwanted goods is free, or what we call free disposal. Consider two goods, X and Y. Suppose we're at point E, which is a bundle of 10X and 10Y. What do our assumptions about preferences tell us about how the consumer ranks bundle E relative to other bundles like F? Since we've assumed more is better, we know that everything to the northeast of E is preferred to E, whereas everything to the southeast of E is worse than E. What about to the northwest? This involves giving up some X, but gaining more Y. If at a point like C, the consumer gets just the right amount of extra Y, so that the extra pleasure from Y exactly makes up for the lost pleasure from less X, we'd expect that the consumer is indifferent between C and E. And there could be many bundles between C and E that make the consumer just as well off as E or C, because we're giving up the right amount of extra Y to make up for the lost X. Sort of a substitution. Similarly, moving to the southeast from E the consumer loses y but gains x, and there will be a set of bundles that are equally good to E. If we connect all the bundles that give the same pleasure as E, we get what we call an indifference curve. An indifference curve shows the set of bundles of two goods between which a consumer is indifferent. A consumer has infinitely many indifference curves, forming what we call the consumer's preference map. Indifference curves have 5 key properties. 1. Bundles on indifference curves further from the origin are preferred to those on the indifference curves closer to the origin. And this is just coming from our non-satiation assumption. 2. Every bundle lies on an indifference curve. This is just coming from completeness. 3. Indifference curves cannot cross. This follows from transitivity. And just as a little outline of a proof here, let's take 3 points, A, B, and C, with an indifference curve that runs through A and B, with C lying above the indifference curve. We know that C is preferred to both A and B. But let's imagine another indifference curve that crossed the first indifference curve and runs through A and C. This would mean that B is less preferred to A and C. But we've already established that it's equally preferred to A, which is a contradiction. 4. Indifference curves slope downward. This just comes from non-satiation. And 5. Indifference curves cannot be thick. And again, this follows from non-satiation. To succinctly summarize a consumer's preference map, economists use what's called a utility function. A utility function assigns a number to every possible bundle of goods, representing the utility of that bundle. The way it assigns these numbers summarizes the consumer's preferences. Namely, if a consumer likes a bundle A more than B, the utility function assigns a higher utility number to A than B. We define a utility function as a function such that if A is preferred to B, then the utility of A is greater than the utility of B. The utility function summarizes the preference map, assigning a number to every possible bundle of goods, assigning higher numbers to bundles that the consumer likes more, capturing the consumer's preference ordering. So just as a little example here, let's look at a famous utility function, one that we've actually already been using, called the Cobb-Douglas utility. Let's let A stand for apples and B stand for bananas, and let alpha equal 1/2. This is difficult to summarize in 2 dimensions, so I'm going to set B equal to 1, and we'll vary different values of alpha. When alpha is very small, increases in A have a relatively small effect on the utility. But when alpha is very large, increases in A have a relatively larger effect on the utility. So let's make the connection back to indifference curves. Here what we've done is introduced a utility function assigning numbers to bundles. And since on the indifference curve, the consumer likes all bundles equally well, it must be that the utility function assigns all the bundles on an indifference curve the same utility level. So if we take a consumer's utility function and set it equal to a particular utility value, we have the formula for one of the consumer's indifference curves. So here we have the formula for the Cobb-Douglas indifference curve for B. As you increase U bar, you get the formula for higher and higher indifference curves. And note that along an indifference curve, B is a function of A. As we change A, B has to change to keep utility constant. So stepping back a little bit, the point of our model is to capture how consumers make choices involving trade-offs. So we want the model to capture how an individual wants to trade off one good for the other. For example, how many X am I willing to give up to get more Y? So that gives us a little definition here. A consumer's marginal rate of substitution is the maximum number of units of the Y-axis good the consumer is willing to give up to get one more unit of the X-axis good. An indifference curve tells us if we add one more unit of the X-axis good, how much of the Y-axis good the consumer can give up and still be no worse off. Put this another way, the marginal rate of substitution is the slope of the indifference curve. At bundles on the indifference curve with small a, the indifference curve is very steep. If we add one more unit of a, the consumer is willing to give up a lot of y and still be no worse off. And on the other extreme, the indifference curve is flat. If we add one more unit of a, the consumer isn't willing to give up much of b. For all the mathematically inclined, you may be guessing that there's a relationship between the marginal rate of substitution and the utility function. And specifically, to get at this relationship, we need to introduce what we call marginal utility. Given some utility u as a function of x and y, the marginal utility of good x is the extra utility the consumer gets from a small increase in x, the derivative of u with respect to x. Just as a note here, the textbook uses the notation u subscript x to stand for the derivative of u with respect to x, which is the marginal utility of x. Here we're going to show that the marginal rate of substitution is related to the marginal utilities of the two goods in a very particular way. First, let's consider a given indifference curve corresponding to u bar. In the background, we have this implicit relationship between a and b, which is our indifference curve. We're going to define this as h, and we're going to substitute this in for b. H is simply taking a and transforming it into b according to the indifference curve. Next, we're going to differentiate both sides with respect to a. And since u bar is fixed, the derivative is 0. And going through and solving for the derivative of h with respect to a, which is our marginal rate of substitution, we get this very particular functional form. The derivative of h with respect to a along the indifference curve is the slope of the indifference curve, or the marginal rate of substitution. So here we've shown that the marginal rate of substitution is equal to the marginal utility of the x-axis good divided by the marginal utility of the y-axis good. The quick way to find the formula for the marginal rate of substitution is to take the partial derivatives with respect to each of the goods and then put them in a ratio with the x-axis good on top. Okay, what else do we need to know to predict actual bundle choices? We've taken as given that consumers choose the best bundle available to them. The notion of best is pinned down by the utility function, as we've just walked through. So next we have to define what's available to them, what we call the choice set, which in turn is defined by the budget constraint. Assuming that individuals can't borrow or save, the budget constraint is implicitly defined by the sum of expenditures. Going back to our two-good model of A and B, with prices set to 1 and income set to 15, our budget constraint looks something like this. Any point on or inside the line represents the choice set, and any point on the line represents full expenditure. Given that we can't save, would we ever choose an allocation that is in the opportunity set but not on the budget line? No. We will always choose a point that's on the budget line. The marginal rate of transformation is the slope of the budget line. In our two-good model here, That's just the price of A divided by the price of B. Before we write down the mathematical solution to the consumer's problem, let's just think about the problem visually. Imagine an indifference curve with points lying below the budget constraint. Let's just pick a point on the indifference curve that's also in the choice set. We can move this point slightly closer to the budget constraint, remaining in the choice set and doing slightly better than before. And remember the marginal rate of substitution happening in the background. If we were to vary the bundle slightly in the region of the original point, the marginal rate of substitution would also vary. Since there's a higher indifference curve running through this new pink point, let's bump up our utility so that the indifference curve runs through this new point. But again, there's still a small region between the indifference curve and the budget line that we can move our point into. And again, we still have some wiggle room for the marginal rate of substitution. At some point though, we run out of space for new preferred points in the choice set and wiggle room for the marginal rate of substitution. And all we're left with is one point at the tangency between the budget constraint and the indifference curve. And this point happens when the marginal rate of substitution is equal to the marginal rate of transformation and the budget constraint is fully satisfied, when we have full expenditure. Here we've glossed over some important details we'll get into in the next videos, but this is the idea for the consumer's problem. We still need to think about what we call corner solutions and think about the shapes of the indifference curves. But what we've introduced here is really the foundation of the consumer's problem and where individual demand comes from.